Alright, so today we're going to start on a kind of new track, and that track is going to be building math from the ground up. Now, one thing you'll quickly realize is that if you try to get to the bottom of math, you'll kind of realize that it's just turtles all the way down. So you have to kind of set the groundwork somewhere and lay a set of axioms. And I'd rather not go all the way down to ZFC just yet. So we're going to start with the naive set theory presentation of things, and that means we're going to define two central kind of starting objects that we're going to base everything on. So first we're going to define what a set is. And a set is collection of things. In particular, we're going to be concerned with asking about two things within sets. The first one is going to be, given some thing labeled X, we want to ask, is X a member of the set? So if this statement is true, then that means X is an element of S, or rather that X is in S. Okay? And so this lets us ask whether or not a given object is in a set. Two, we can also talk about relationships between sets themselves. So given two sets, we'll call them capital X and capital Y. We want to be able to ask questions like, is X a subset of Y? So this symbol right here is going to be the subset symbol. And this means, in a formal and mathematical way, for all lowercase x inside capital X, that object labeled by lowercase x is also in Y. So, in other words, X contains only things that are elements of Y. Okay? So for example, if I have a collection of numbers, maybe 1, 2, and 3, if I then have a smaller collection of numbers, maybe this one only is 2 and 3, well, this one is clearly a subset of that because every number that's in this set is also in that set. But that doesn't necessarily mean that everything in Y is also in X, just that everything in X is also a member of Y, and this subset relationship makes that explicit. Now, the second kind of entity that we're going to define is that of a function. And we're typically going to write functions like this. We're going to say that function colon some set arrow to another set. And what this is saying is f takes inputs from S and gives outputs in T. Right, so that we're guaranteed for all S, lowercase s from capital S, f of lowercase s is going to be an element of T. And that's what this definition is. So we're going to think of functions as things that are basically transforming things from S and giving us back out something in T. Now, it could very well be that S and T are the same thing, and we'll examine that now, actually. So one of the things that we want to do as we try to kind of build math from the ground up is we want to revisit all the things that we learned in grade school about math and put them into a more formal but also a more abstract context. And the thing that we're going to start with is the thing that started it all, counting. Right? We are going to define the natural numbers. the natural numbers, in other words, the counting numbers. And what we're going to do is we're going to talk about the set of natural numbers given by this blackboard bold n. Okay? And we're going to define the natural numbers by making sure that they have 3 properties. And property 2 really has kind of 2 sub-properties within it. So we're going to leave a little extra space, and down here is going to be property 3. Okay, now let's think back to first grade or kindergarten, or probably most likely your parents, right? What did they teach you about counting? They probably taught you to start counting from 1, but for purposes which will become which will be revealed later, we're going to start counting from 0. And that is, in fact, our first property of the natural numbers as a set. We're going to say that there is a special element inside the natural numbers that we're going to label with the symbol 0. So there exists some element inside the natural numbers, and we're going to call it 0. And I'm not going to tell you anything about 0, so forget about all the properties of 0 that we already know, because the point here is that we're actually going to build them from the ground up instead of just arbitrarily declaring that they're true. We want to kind of minimize the number of things that we're just going to arbitrarily declare to be true, this being one of them. There's a thing inside the natural numbers called 0. Secondly, there exists, and this is the reason why we wanted to introduce the notion of functions, is because we're actually going to define one property of the natural numbers in terms of a function that exists, that takes natural numbers as input and gives natural numbers as output. Such that, and we want this function, which is a lowercase sigma here, to have 2 special properties. The first one is that for every natural number you can think of, so for all lowercase n inside this fancy uppercase n, for all natural numbers, sigma of, for all pairs of natural numbers, n and m, rather, and let's clean this up a little so it doesn't look so messy. So we're going to think about all pairs of natural numbers n and m. If I know that sigma of n is equal to sigma of m, that is, the output I get when I plug n into sigma is the same as the output I would get by plugging m into sigma, well, that guarantees, and this is a property that sigma has, we're not going to prove that this is true, this is something that we're going to assume is true of sigma, then n necessarily equals m. Let's move on to all the properties, and then we'll kind of fit them together into why this is the way that we're going to choose to define the natural numbers. So for anyone familiar with dealing with functions and all the kind of interesting properties that they might have, we're going to say that this means sigma is injective. And what we've actually written here is the definition of an injective function. That means that given 2 inputs, n and m, into the function, if their outputs are equal, then the original inputs themselves must also have been equal. And this is the functions that have this property are called injective. Now, for example, there are functions which don't satisfy this property, and it's worth calling out functions that do, because we don't necessarily know that every function does. So, for example, take the absolute value function, right? Something that maps, say, the absolute value of -3 is, well, +3. But that also happens to be the absolute value of +3. So that means that the absolute value function is not injective, because even though we supplied different inputs into it, we got the same output. And what an injective function really is it's the guarantee that, well, if the output is the same, then the inputs must have been the same. And clearly the absolute value function does not satisfy that. So back to what we were talking about, sigma, which takes natural numbers as inputs and gives natural numbers as its output, is an injective function. Secondly, for all natural numbers, if I feed such a natural number into sigma, I'm guaranteed not to get 0. And looking just a bit further ahead, this means that no natural number counts up to 0. When we're going to see later that sigma is going to be our counting function. But first, we're going to define property 3 before we really see how all these properties kind of fit together. And it's really by considering all these properties together that we realize how these 3 things really capture the intuitive idea of counting without relying on first defining what numbers are. In some sense, the only properties that we're going to ascribe to numbers is what we can do to them. And that's what sigma is here to do. So the third property is about subsets of the natural numbers. Given some set S, which is a subset of the natural numbers, right? If we know that 0 is in S, is an element of S, and this is the logical AND symbol, just for clarification. If I know that 0 is in S, and for every natural number in S, we know that sigma of n is also in S, then these two conditions, if I know they are both true at the same time, will together imply that S is not just a subset of the natural numbers. It doesn't just contain some of the natural numbers. It in fact contains all of them. It is the set of natural numbers. Now, why did we pick these 3 things? Well, the idea is, first off, we're going to start counting at 0. That's just kind of an arbitrary rule we're going to decide on. You could start counting at 0 or you could start counting at 1, but for this purpose and this particular system of axioms was it's a little bit messy. This particular system of axioms is called the Peano Axioms, and they were specifically designed to capture intuitive but abstract properties of the natural numbers. What does it mean for this to be the set of counting numbers, the set of things that we use to count? Well, first we're going to start counting at 0, meaning, if I'm counting rocks and I happen to not have any rocks, right, I've got 0 rocks. So counting really starts from not having any amount of whatever thing you're counting. We're going to use sigma as the counting function. Now, what kinds of properties should our counting function have? Well, for one, let's say given any natural number, right? Maybe 5, just as an example. If I know that I have a mystery number x, and I say that if you count up from x once, and you'll get 5. This should be a statement that uniquely defines x, right? So our counting function should be something that doesn't cycle back to a value that we had before. Imagine if instead our counting function could give the same value for 2 different numbers. That means I could get 1, 2, 3, right? And so it's really sigma that's taking 1 and outputting 2. It's sigma that's taking 2 and outputting 3. Let's say somehow miraculously if I then apply sigma again, and I get back the number 2, well, then I'm not really counting up, right? The idea is that every time we count up, our number should be increasing. We shouldn't end up revisiting a number we've already hit. And so that's what property A of sigma is intended to capture. Now, what does property B capture? Well, it says that nothing counts up to 0. Again, just think if we were to start just counting from 0, 0, 1, 2, 3, so on and so forth, right? As I successfully count up to higher and higher numbers, if I were to suddenly wrap back to 0, well, I'm not really counting the way that we expect counting to work. And again, we're not going to try to provide some kind of super high-level justification, right? This should agree with intuitive notions of counting that we should get. Okay, so then number 3 definitely looks like the most abstract of them all, right? It's a statement about how subsets of the natural numbers are ultimately the whole set of natural numbers. Well, what this is really supposed to capture is, 1, counting starts from 0, which we've already stated here, and I'm going to delete that. Counting starts from 0, which is a property we've already stated. And this is a statement really about what the natural numbers are, right? This is a statement that says, consider the set of things that you can reach using only this process, right? And that's what S is really intended to capture. We started counting at 0, right? So 0 is an element of S. Okay, well, if this criterion is also true, then that means since 0 is in S, we know that sigma of 0 must also be S, must also be in S. Well, sigma of 0, sigma being the count up by 1 function, just gives us 1. And so 1 is also in S. But since 1 is in S, the fact that this criterion is true, again, we just apply this again, and we get, well, sigma of 1, which is 2, is also in S. But that implies that sigma of 2, which is equal to 3, is also in S, and so on and so forth. So what is S really? S is really the set of all things that we can get by starting from 0 and successfully counting up by 1. Parentheses, we need to finish that with a quote. So, the set of all numbers that I can reach eventually by starting from 0 and continuing to count up by 1. Well, that's exactly how we want to capture what the counting numbers are. And so we introduce axiom number 3. For those of you who have done proofs by induction before, you'll notice that this is very similar to what is needed to show that a statement is true via induction. And so, in fact, it is that in the system of the Peano axioms, induction, which is this step 3 right here, which is also itself known as the axiom of induction. Induction, we're going to assume by this axiom, works. And in the next video, we're going to see how we can use these 3 properties of the natural numbers to start proving other things. And to give just a little bit of a teaser, since we're building math from the ground up, and we've only defined counting so far, we have yet to define even addition or multiplication. And in the next video, that's exactly what we're going to do. We're going to define addition using these 3 axioms, and we're going to see how familiar properties of addition will materialize via these definitions.